Good day, everyone. This is a refresher course on signals and systems, which is meant to serve as a summary review of the course. So we are going to be having a series of lectures to revise the course curriculum. And to begin, we understand that the engineering and science discipline forms a body of signals and systems. So whichever way is either we want to figure out the response to certain excitations, or better still, figure out how to design a particular system to provide a desired response given certain levels of excitations or input. So therefore we attempt to analyze or develop, or better still process an entire system or the signal itself such that the desired outcome is generated. So regardless of the nature or type of signal and system, the idea behind analyzing, or better still synthesizing the entire system becomes the business of the engineer or the scientist. So to begin, what is a signal? So we understand that a signal is an abstraction of any measurable quantity that is a function of one or more independent variables, such as time or space. So, in other words, we have an independent variable, which could be time, which could be space, and then we want to match it with respect to certain quantities. And an example is the alternating current. And we say that an alternating current, or an AC, is a signal because the current varies with time. So in other words, the quantity here is the current, and we observe that the value of this quantity, which is current, varies with time. It changes with time. So that qualifies it to be classified as a signal. And conversely, a direct current is not a signal because the current is constant with respect to time. It doesn't change or vary. So in analyzing signals, it is quite interesting to know that a signal could either be a single variable signal or a multivariable signal. So what is a single variable signal? It's a signal that depends on a single variable, say x or t. So here we have some examples, probably f of x, f of t, it could be h of t, it could be k of m, But the most important thing here is that it depends on a single variable. And the other case is the multivariable signal, which depends on two or more variables. And as examples here, we have f of x of 1, x of 1 rather, and s of 2, meaning this quantity depends on two different variables, x of 1 and x of 2. And we also have another, which could be f of t sub 1, t sub 2, t sub 3, t sub 4. And here we have this quantity to, be dependent on four independent variables, which is the T1, T2, T3, T4. And the list is endless. But the important thing here, or the important thing to note here, is that once we have multiple independent variables, then that signal becomes a multivariable signal. But on a general note, or in a general note, or better still, broadly speaking, signals are classified into two major broad categories, which is the continuous time signal and the discrete time signals. So when we talk about continuous time signals, we say these are signals that are present for all instant of time or space. Examples could be the sinusoidal signals, the cosinusoidal signals, the triangular waveform, the rectangular waveform, and here what do we have? Oh, we have a rectangular waveform here. And you see that it varies over a given range of negative infinite time to positive infinite time. Okay, so with an amplitude of A. So here, the signal x of t has a value for every value of time t. Okay, so that makes it a continuous time signal. It is continuous. There is no break in its continuity. Let's put it that way. And the second category is the discrete time signal. And this is a signal that is only present at discrete points in time. And here's an example. And you see that we either have a signal at t sub naught, t sub 1, t sub 2, or t sub minus 1, t sub minus 2, and on and on. So x of n here can take on discrete values. And this is very important in signal processing and analysis when we talk about sampling. Okay, but well, we'll leave that for some other lectures. But for now, it is important to know that we have two broad categories, the continuous time signals and the discrete time signals. While the continuous time signals vary, take on values regardless of the time parameter. In other words, for every instant of time, for every given time interval, there is a value tied to it. But for the discrete time signal, well, it takes on values of the signal at specific points of time, not for all time. Okay? Okay. So what is a system? Now, a system is an abstraction of anything that takes an input signal, operates on it, and produces an output signal. And one perfect example is a human being. So with the brain, it could operate on any given signal, be it visual through the eyes or sound waves through the ears, or even, through the nostrils, smell, then through the tongue, taste. The bottom line is, regardless of the type of signal, there is a part right there in the human anatomy, the brain processes it, and then it gives an output. It's a response to pain, to touch, and all of that. So, well, that's one of those systems. But coming to the engineering and the engineering and science discipline, we have quite a number of systems, and it is our business and our job in the engineering discipline to design the systems. Okay, so you should know that a system will be meaningless. We have no particular significance if there is no signal to be operated upon. So for a system to perform any meaningful operation, there must be an interface with a signal. And this is a typical example of a system. So we have the input signal coming into the system, then we are expected to generate an output signal. So the output signal is going to be dependent on the nature of the system. Okay. So just like signals, systems could be broadly categorized as either continuous time systems or discrete time systems. So for a continuous time system, we'll say such a system operates on continuous time signals. While For the discrete time systems, they are systems that operate on discrete time signals. And one good example of a theoretically achievable system is the linear time invariant system. Now, although the inverse may be true in practice, the LTI system, which is the linear time invariant system, provides sufficient approximation for the realization of such systems. Okay. So, what are LTI systems? Now, from the word linear and time invariant, it means that this system operates based on two fundamental principles: linearity and time invariance. So an LTI system or a linear time invariant system combines the properties of linearity and time invariance. So when we talk about linearity, assume we have two separate systems. Here we have the first system, which takes on an input x1 of t and then produces an output y1 of t. And then if we have another system, or better still, another signal operating in that same system, say S2 of t, and then it produces an output y2 of t, should we superimpose these signals by way of summation and then pass it through the system, we're expected to have an equivalent signal. Okay, such that x1 of t plus s2 of t should give us y1 of t plus y2 of t. Now, it's that simple. So in other words, the specific input produces a specific output. Okay, now for the time invariance property, if we have a system where we feed in an input s of t, we're expected to get an output y of t. So should there be a shift in time, then such delay in the input will be seen also at the output. Meaning, should I transmit a signal s of t some 10 hours from now, I should receive y of t. The only addition here is that it will be delayed for those hours. Meaning the parameter or the properties that describes the signal does not change with respect to time. So in other words, here I am, Augustus Ivaze. So it is expected that some 10 years ago, Augustus Ivaze should be the same Augustus Ivaze today. Okay? And the only thing that must have changed should be time. But we know in reality, we really don't get such systems because human beings change with time. So they are not linear time invariant systems. Oftentimes, what we get into our systems begin to change us, the environment changes us, so many things changes us, or even friends, family, a couple of factors that could alter the way one could react to a particular incident over time. Probably, depending on the state of your mind. What you laughed over yesterday, you may frown at it today. So meaning you are not linear, you are not a linear time invariant system. You are a linear time variant system. But for a linear time invariant system, we expect that the performance of the system, or better still, the properties, let's put it that way, that's a better word. The properties of that signal should not change with time, but should it be delayed in time, then we should experience an equivalent delay in the output. But S of t should give us y of t. So in other words, when we have S of t delayed by some time tau, then the output should produce a y of t delayed by some amount of time tau. Okay, so that makes it a linear time invariant system. And we want to use the likes of automobile. Okay, if everything is okay, You should ignite the engine at some point in time, and it should respond and take you to wherever. Should things change, then it means the system is beginning to fail. But if the system is not failing, then it should give you the desired output for a given input. Okay, so this is quite uh, interesting to us because in our study, we'll be considering the linear time invariant system. But how do we translate this in terms of reality? Because a couple of systems in the real world are not LTI systems. But what we want to say here is that the LTI system provides sufficient approximation when we now have to analyze systems that may not be LTI, to be specific. Okay, so summarily, the time invariant system is one that responds the same no matter at what time the input is applied. So, from all of this, what is an LTI system? So, this is what we get. So, given an input S of t into an LTI system whose property is described by some parameter h of t, then we should have an output y of t for which S of t convolves with the parameter of the system, h of t. So here, S of t is the applied input signal or the excitation, and y of t is the expected output signal or the response. And the h of t is the impulse response of the system. So it is a parameter that characterizes the system. And then we have the convolution operator, the asterisk sign, which is the convolution operator. And it is a tool for the time domain analysis of the system. Okay. Now, well, we've said so much. We've said a lot of things already. And I think it would be worthy of note to summarize what the study of signals and systems is all about. So when we talk about signals and systems, yes, we've practically gone through what we have to talk about, but what are the major concepts we get to study in this course? Okay. So the basic concepts under consideration in the study of signals and systems are: one, the description of signals as function of frequencies. Now, you'll see for an LTI system, we have the impulse response, h of t, such that the relationship between the input s of t and y of t is now s of t convolving with h of t. And to analyze the system may somewhat be a daunting task. And then for us to be able to analyze this, we want to represent this system, which is in the time domain, in its frequency equivalent domain, so as to ease the analysis of the system. And to further analyze the system, things that we'll be talking about much later, you see that we take the transfer function, so relating the output to the input, and then we'll get the transfer function, which is now h of s in the s domain, and we know it's a function of the sigma and the j omega, which is the attenuation and the frequency component of that signal. And voila, that brings us to the study of Laplace transform. And when we now have to study the level of convergence, then we'll begin to talk about the Fourier transform, and on for the continuous time system. And for the discrete time systems, we'll begin to talk about the discrete Fourier transform, and the fast algorithm being the fast Fourier transform, and on. Okay, Z transform also, which is equivalent, the discrete equivalent of the Fourier transform, which is for the continuous time signal. Well, all of those for the analysis of signals. Okay, then we'll also talk about some basic properties of systems. Okay. Now, okay, let's go on. So we want to describe signals as functions of frequency to enable ease of analysis, and also want to investigate how systems respond to inputs of different frequencies. Okay, so if I excite a system at, say, a given frequency, and then alter or change the frequency value, now what is going to be the impact of the system on these variations? So we also want to investigate such in the study of signals and systems. And then next, we want to provide tools for switching between time domain and frequency domain representations. Just like I said earlier, we want to get a transfer function of the system, then we have to move from the time domain. And then we need to get parameters, tools, and some of which are the Laplace transform, the Fourier transform, the Z transform, So we want to provide tools for switching between these domains, between that time domain, frequency domain representation, depending on which is convenient. And then we also want to determine which domain is suitable for a particular problem, just like I mentioned earlier. So we don't just want to dive into a problem but we want to tell which domain. Is it the frequency domain? Is it the time domain? And then, so I think these four concepts, describe, or better still define, the requirement or the goals or the objectives of the signals and systems course. And well, not to take too much of our time today, here we'll be talking about the problems in signals and systems. And I think this should just be a nice place to stop today. And then we figure out some other time to pick things up from where we stop. And what are the major problems in signals and systems? Well, here we have two major categories. The first is analysis problem. So in analysis problem, we want to figure out the expected response in a system. So meaning, given a certain line of excitation to a system, then what is going to be the response? So it means we know what the signal is, we know the system parameters, and then we want to figure out the output. So we have that in red star. Okay, so that is the major consideration in the analysis problem. So given the system, we feed it with the input, which is the excitation. Then we want to tell how is this output going to look? How is the response going to look? This is the analysis problem. And the second problem we encounter in signals and systems is the synthesis problem. And here we have an idea how the input, or what the properties of the input are. And also we know what the output should be. But how do we design the system that will give us that desired output? So this is synthesis problem. So we want to figure out the system. We want to tell, okay, this is how the system should be, and these are the parameters, okay? And then, that leads us to wanting to figure out the properties that makes up that system itself. Well, synthesis problem, I say, is should be beyond the scope of the undergraduate course, but whichever way, it is the problem of an engineer or a scientist to solve. Okay, so let's assume we want to get a desired output given a desired input for an electrical system design. So we want to tell the properties of the circuit. Okay, so is it going to give us a first order system. When we try to analyze the transfer function, is it going to give us a second order system? So we want to begin to analyze the poles and the zeros and all of that. So things like that leads us into synthesis problem. It could be complex, but with that, we are able to tell the particular system in terms of optimizing that system to achieve the given output, having that input. So I think this is where we'll stop today. So I want to say thank you for taking this course and hope to see you in our next class. Bye.